Hello and welcome to my talk. Today I'll be discussing our work on measuring the carbon intensity of AI systems in cloud instances. This is joint work between the Allen Institute for AI, where I am, Microsoft, the University of Washington, Hugging Face, Carnegie Mellon, and the Hebrew University of Jerusalem. The field of AI has seen remarkable progress on a broad range of tasks in recent years, partly driven by increasingly large models trained on increasingly large datasets. Here in this plot, we can see the number of parameters over time for some of the largest models announced. I took this plot from a Microsoft blog post from a couple years ago, but this trend hasn't slowed down. Of course, more recent models like GPT-3 and those trained by DeepSpeed are in fact way off this scale. In addition to individual models growing, the number of research projects in our field has also grown. Here we see the number of submissions to ICLR, NeurIPS, and ACL over the past few years, and you'll see that between about 2017 and today, we've more than doubled the number of submissions. An increasingly large number of these papers are supported by experiments in the cloud. Of course, industry use of the cloud is likely even greater, but here we have information about the academic conferences. According to recent estimates, data centers make up about 1% of global electricity demand. Recent paper checklists have also specifically called for reporting CO2 emissions, likely from using electricity in data centers, but this information primarily hasn't been available to users. Carbon intensity of electricity is how much CO2 is emitted for each unit of electricity consumed. In this work, we provide methodology for how to calculate carbon intensity of AI workloads, and we provide some of the first direct measurements of common models' AI carbon intensity. For this work, we partnered with Microsoft Azure to get access to the necessary information. So on the next few slides, when you see measurements, remember that these measurements are in that particular cloud. Okay, so here's an outline of what we will be discussing in this presentation. First, we'll go through some methodology for how you compute the carbon intensity. Then we'll talk about some results. We'll go over some optimizations of what we can do to help mitigate some of these emissions, and finally, future directions. So first, methodology. Of course, we aren't the first to measure emissions. Previous work primarily falls into two camps. The first analyzes some previously run large experiments, like the pioneering work of Strubell et al. And the second camp introduces some kind of tool that is designed to facilitate reporting of emissions. Two of the closest tools are CodeCarbon and EnergyViz. CodeCarbon is a Python package, which we actually recommend to users that are not using cloud instances, but it doesn't have privileged information about the specific region, for example, that the cloud instance is running in. It also calculates, both of these calculate the average electricity usage from your AI workload, and then the average carbon intensity of the electricity in your broad region, and then multiplies those two numbers together to give you your estimate, but this doesn't capture the change over time in both of those. Okay. Our approach starts by measuring electricity consumption of the GPU specifically. Most electricity consumption of AI workloads is from the GPU. For example, we ran an experiment training BERT on a Titan X GPU, and we estimated about 75% of the total electricity consumption of the system was just from the GPU. So that's what we focus on. Importantly, electricity consumption is a time series, represented here with this illustrative plot. The plot isn't an actual measurement, but it's meant to convey the idea. Here, emissions per kilowatt hour are also a time series. You might see this kind of plot if the demand for electricity is higher during the day than at night. So supplemental electricity generation is used during the day, while overnight only the most efficient power generation is used. Next, we align these two time series, and this provides an emissions estimate for your workload in your region. In this paper, we evaluate a variety of regions. And the key idea here is this provides measurements of what your emissions would have been if you had run this experiment in the different regions evaluated. Our goal is to provide useful measurements to a reader, and this simulates the decision an AI practitioner might need to make when deciding on the particular region to run their experiments. And I will note this methodology primarily comes from the Green Software Foundation. Okay, so we've talked a bit about our methodology. Let's dive right into some results. In this plot, we explore two questions. First, how much variation is there between different regions and at different times of year? We evaluate 16 different regions around the world, and we see that what the emissions would have been if BERT had been trained in those different regions throughout the different times of year. Recall, this is just electricity consumption from the GPU, and it doesn't account for things like data center cooling or other components of PUE. So this is likely, almost surely, this is an underestimate. Our takeaway is that the region matters a lot. The time of year does see some variation, but it really depends on the region, and the difference between the different regions is significantly greater. We also evaluate training our models at different times of day, and I encourage you to check the paper for more detail on that. Here, what we see is the most efficient region would lead to about a third of the emissions of the least efficient region. Importantly, we argue this is useful information to the users, and so cloud compute providers should be providing this information to the users who have to make the decision about what region to run their experiments. Using our methodology, we provide some of the first concrete measurements of the emissions for training a variety of AI workloads, including fine-tuning BERT here on the far left, language modeling with BERT, language modeling with a 6 billion parameter transformer, 3 sizes of DenseNet, and 5 sizes of vision transformers. On this plot, we show a vertical blue bar for each model, which represents the range of emissions across regions and times. Imagine the info on the previous slide is represented in each blue bar here. The top of the blue bar is the largest emissions, the light blue regions are the first and fourth quartiles, and the black is the average. We can see the largest training runs release a significant amount of emissions, no matter the region. Our training run of the 6 billion parameter transformer emits around the same amount as the average US home does in a full year. And we only trained this model 13% of the full training run. So training this model to completion from scratch would actually emit about an order of magnitude more emissions. The smallest experiments here we see emit very little. The DenseNet models are about the same as charging your phone. So our takeaway here is that the emissions are dominated by the largest experiments, and thus the responsibility for transparency falls on those experiments. Okay, next we'll talk about a couple optimizations that the cloud compute providers can do to help reduce these emissions. Here we'll explore two approaches for reducing emissions. First, what we call the flexible start. This figure, again, represents our time series for emissions per kilowatt hour in a particular region. You could imagine, again, the peaks here are during the day where demand for electricity in the region is greater, and overnight you've got those valleys where only the most efficient power generation is used. We explore workloads here that have a flexible start time. So imagine your workload has some duration and you want to run it during the day because that's when you're working. If this is a regularly scheduled workload, you instead might be able to run it at a different time, like here, or potentially here, where the average emissions per kilowatt hour are lowest. What we find is that using this approach, finding the best possible start time over a 24-hour period for a given job, This can reduce a lot of emissions for especially the shorter jobs. It's less effective at reducing emissions for the jobs that run for more than a day, which is intuitive because those longer jobs average out the 24-hour variation that you see anyway. For our second optimization, we consider pausing and resuming the workload depending on the current emissions. This is similar to spot instances, where users set a cost threshold, and when the cost goes above that threshold, the instance pauses. Here, the threshold is on the emissions per kilowatt hour. This is particularly useful for AI workloads that have flexible durations. If you're regularly retraining models on new data, this could be a good option. If we use the pause and resume algorithm such that the total duration of training is doubled, what we find is that this, in fact, doesn't help that much for smaller training runs like the DenseNet models. But on the other hand, this is one of the most effective approaches for those longer training runs, like the 6 billion parameter transformer. This is the opposite of what we found on the previous slide. Here, I will highlight that the information I'm presenting is just a subset of all of the experiments that we ran. We have a much more thorough analysis in the paper, and I encourage you to check it out. Finally, I'll discuss some future directions. So first, we hope that our analysis will be part of an operational life cycle for machine learning systems. Of course, we need more data. We need information about PUE, but also we just looked at training, and of course, the inference and the number of times a model is applied to new data after it's trained need to be accounted for. When choosing a region, there are three considerations that most users have. First is cost, second is data transfer speed, and third is emissions. When the cost is roughly equivalent and the data transfer speeds don't matter as much, so you're not building some kind of interactive system, for example, we hope users choose to minimize emissions. Of course, this can only happen if they have access to the information about the emissions from the different regions. We note here that the application of the AI itself really matters because we don't think this analysis can be done in isolation. It is important for us to consider what the AI system is actually used for. There are some great applications that can help combat climate change, and there are also lots of applications that would exacerbate it. Finally, I will note there's a lot more takeaways and conclusions in the paper, but here really the responsibility of transparency and potentially buying carbon offsets does lie with the largest experiments. That's clear from our results. Again, check the paper for more. Thank you.